When your eyes rise toward the night sky, what you see feels endless pinpoints of light scattered across a vast black canvas. Yet this familiar vision carries a hidden truth. Nearly every star your eyes can perceive belongs to a single cosmic home, the Milky Way. Our galaxy is not alone. But it is part of a quiet gathering, about 50 neighboring galaxies bound together in what astronomers call the local group. This is not a tale of unreachable realms at the edge of existence. This is about where we stand. These galaxies are near enough to be examined closely, near enough for their gravitational pull to matter, and near enough that some are destined to merge with us. The local group spans roughly 10 million light-years, forming a small but meaningful domain in the larger universe. A light-year marks how far light travels in a single year, racing through space at 186,000 miles per second. In that time, it covers nearly 6 trillion miles. Multiply that by 10 million, and the distance becomes almost unimaginable. To simplify the scale, imagine compressing the entire observable universe down to the size of Earth. In that model, the local group would shrink to something no larger than a modest house. This is a quiet inlet within a boundless cosmic sea. 3 immense spiral galaxies shape this region. One of them is our own Milky Way, a vast system containing hundreds of billions of stars along with their planets, moons, asteroids, comets, and immense clouds of gas and dust. Its structure includes a central bar, from which graceful spiral arms sweep outward into space. Our Sun resides about 26,000 light-years from the galactic core, tucked within a smaller branch known as the Orion Spur. Picture the galaxy as a living city. The center pulses like a crowded downtown, dense with stars. Farther out, where we exist, space opens and thins. From end to end, the Milky Way stretches roughly 100,000 light-years across. Yet its disk is astonishingly thin, only about 1,000 light-years from top to bottom. Scaled down to the size of a dinner plate, it would be thinner than paper. This vast structure was born around 13.6 billion years ago, shortly after the universe itself ignited. Over time, it grew not gently, but through consumption. Smaller galaxies were pulled apart, their stars stripped and absorbed. This is not symbolism, it is the raw mechanics of gravity shaping destiny. Beyond our galaxy lies Andromeda, also known as Messier 31, the largest presence in our local family. Sitting about 2.5 million light-years away, it is astonishingly close by cosmic standards. On a dark, clear night, it appears as a faint blur to the naked eye. The light reaching you from Andromeda began its journey when early humans were just learning to shape stone tools. Andromeda holds close to 1 trillion stars. It's giving it more than twice the mass of the Milky Way. Its disk spans about 220,000 light-years, dwarfing our own in size. Like the Milky Way, it is a barred spiral galaxy, though its central bar hides more subtly from view. At its core lies a supermassive black hole, weighing over 100 million times the mass of our Sun. The third great presence is Triangulum, or Messier 33, located roughly 3 million light-years away. It is smaller than its 2 companions, yet it remains one of the dominant members of the local group. Unlike the other 2, Triangulum lacks a central bar. Its spiral arms flow directly from its core, uninterrupted and elegant. Triangulum contains around 40 billion stars and measures about 60,000 light-years across. Though modest in size, it radiates beauty. Its spiral arms are sharply defined, glowing with regions of active star birth. Compared to its mass, it forms new stars more energetically than either the Milky Way or Andromeda. Surrounding these 3 giants are dozens of smaller galaxies scattered like quiet witnesses between them. Our dwarf galaxies small, faint systems that vastly outnumber larger ones. They hold essential clues to how galaxies are born and transformed over time. Some are smooth and rounded, known as dwarf ellipticals. Others are even more diffuse, appearing nearly shapeless dwarf spheroidals. Still, others are chaotic and irregular, continuing to forge new stars amid disorder. Though their forms differ, all dwarf galaxies share one defining trait: they are ruled by dark matter. This unseen substance makes up roughly 85% of all matter in the universe. Silently guiding the structure and fate of everything we observe, we cannot perceive it with our eyes because it gives off no light, absorbs none, and reflects nothing back to us. yet its presence is undeniable. Its influence reveals itself through gravity. When astronomers track the motion of stars inside dwarf galaxies, they discover something unsettling. Those stars are moving far too quickly to be bound by the gravity of visible matter alone. Something unseen must be adding weight. Its hidden mass is dark matter, and the imbalance is extreme. In many dwarf spheroidal galaxies, dark matter outweighs normal matter by hundreds of times. In the faintest and most fragile systems, the ratio can climb to nearly 3,000 to 1. These galaxies are not built of stars with dark matter mixed in. They are vast reservoirs of dark matter, lightly dusted with stars. Because of this dominance, dwarf galaxies become sacred testing grounds for one of the universe's greatest mysteries. Scientists aim gamma-ray telescopes toward them, listening for faint whispers of energy that could appear if dark matter particles collide and destroy one another. No unmistakable signal has yet emerged. Still, the watch continues. Most dwarf spheroidal galaxies are ancient relics. They were born more than 10 billion years ago and ceased forming stars shortly thereafter. Their skies glow with old red stars. While youthful blue stars are almost entirely absent, somewhere in their early history their ability to create new stars was extinguished. The leading explanations suggest several forces acted together. To begin with, these galaxies possess weak gravitational grip when the first massive stars ignited and later detonated as supernova. The released energy may have been enough to expel the remaining gas, entirely stripping away the fuel required for future generations of stars. Next came the early universe itself, during a phase known as reionization. Intense ultraviolet radiation flooded space within the first billion years after the Big Bang, heating gas inside small galaxies until it could no longer collapse into stars. Finally, environments sealed their fate. As dwarf galaxies drift close to giants like the Milky Way or Andromeda, powerful interactions unfold. Tidal forces peel stars away. Hot gas surrounding the larger galaxy sweeps out cold gas from the dwarf through ram pressure. Radiation from the massive host heats and ionizes what remains. Star formation is silenced. What is left behind are dormant systems, cosmic fossils preserved from the universe's youth. Their stillness is precisely what makes them so valuable. Their stars formed when the universe was young and chemically simple. By analyzing the elements locked inside those stars, astronomers trace the long transformation from the original hydrogen and helium of the Big Bang to the complex elemental richness seen today. Our own galaxy is surrounded by dozens of such companions, between 50 and 60 satellites identified so far. The most familiar are the large and small Magellanic Clouds. From the southern hemisphere, both are visible without telescopes, appearing as detached misty fragments of the Milky Way itself. The large Magellanic Cloud lies about 160,000 light-years away, holds roughly 30 billion stars, and spans around 14,000 light-years. The small Magellanic Cloud is more distant, about 200,000 light-years away, and far smaller, with only a few billion stars. Both clouds are irregular in shape and bursting with star formation. For decades, astronomers assumed they were permanent companions of the Milky Way. New evidence now suggests otherwise. They may be visitors, passing by our galaxy for the first time, and that passage may prove fatal. The Milky Way's gravity is already stretching them, drawing long streams of gas away. In time, they are likely to be dismantled and absorbed. One dwarf galaxy is already deep into that fate. The Sagittarius dwarf elliptical lies about 70,000 light-years from the galactic center. On the far side of the Milky Way, it has plunged through our galaxy's disk multiple times. Each encounter strips more stars from it, leaving behind immense stellar streams that coil around the Milky Way like ghostly ribbons. These crossings do more than steal stars. They send waves through the galactic disk, ripples spreading outward like water disturbed by a falling stone. Such disturbances can spark new star formation, and may even subtly alter stellar orbits near our own sun. Some researchers believe one such passage occurred around 300 million years ago, possibly nudging the solar system's path around the galactic core. In the distant future, the Sagittarius dwarf will vanish completely, dissolved into the Milky Way. Only the unique chemical fingerprints of its stars will remain as proof it ever existed. Farther out still lies the Fernax dwarf spheroidal galaxy. resting roughly 460,000 light-years away another silent witness from the universe's earliest age. What sets Fernax apart is something rare for a galaxy so small. It carries 6 globular clusters. These clusters are tightly bound spheres of stars, containing hundreds of thousands, sometimes millions of suns crowded into regions only a few dozen light-years wide. They are among the most ancient structures known, survivors from 10 to 13 billion years ago. For a dwarf spheroidal like Fernax, this number is extraordinary. Most galaxies of its kind possess none, or at best a single cluster. The presence of 6 points to a deeper truth. Fernax was not always what it is now. Long ago, perhaps 10 billion years in the past, it may have been 10 times more massive, so with enough gravitational strength to create and hold on to these stellar relics. Over immense stretches of time, as Fernax circled the Milky Way, tidal forces slowly peeled away its outer layers. What endured were the globular clusters, compact, resilient, and unchanged. They stand like sacred remnants, bearing silent witness to a galaxy that was once far greater than what remains today. Another ancient system, the sculptor dwarf spheroidal, lies about 290,000 light-years away. Discovered in 1937 by Harlow Shapley, Sculptor contains only a few million stars, all of them old. For more than 10 billion years, no new stars have formed there. Though quiet and dim, Sculptor holds immense scientific power. Its stars preserve the chemical record of the early universe, frozen in time. Andromeda, like the Milky Way, commands its own retinue of satellites, at least 35 of them. It's just 22,000 light-years away. It holds several billion stars compressed into a remarkably small space, making it one of the densest galaxies known. Such density hints at a violent past. 32 may be the exposed core of a once large spiral galaxy that ventured to near Andromeda long ago. Gravitational forces stripped away its arms, disk, and halo, leaving behind only the hardened heart. Another companion, NGC 147, sits about 2.7 million light-years from the Milky Way. It appears to be slowly surrendering to Andromeda's pull. With each orbit, energy is lost. Each pass tightens the spiral inward. In a few billion years, NGC 147 will likely be torn apart, its stars absorbed into Andromeda's growing mass. Beyond the satellites of the 3 dominant spirals, the local group contains lonelier members drifting between the giants. IC-10, a dwarf, irregular galaxy about 2.2 million light-years away, lies roughly between the Milky Way and Andromeda. It is alive with creation, forming stars at one of the highest rates per unit mass in the entire group. IC-1613, another dwarf irregular, located around 2.4 million light-years from us, appears to be interacting with intergalactic Gasson encounter that may be awakening new star birth. Farther out, near the edges of the local group, lie Sextans A and Sextans B, about 4 to 5 million light-years away. Both continue forming stars, though more quietly. Sextans A's stretched shape suggests it was disturbed by gravity long ago. Then there are the faintest members of ultra-faint dwarf galaxies discovered only in recent decades. These include Segway 1, Segway 2, Willman 1, Boats I, and Boats 2. They exist at the very threshold of what qualifies as a galaxy. Some contain only a few thousand stars. Segway 1, identified in 2006, lies roughly 75,000 light-years from the Milky Way and holds barely 1,000 stars. At first, astronomers questioned whether it was a galaxy at all or merely a globular cluster. The answer came through motion. Stars move too fast to be bound by visible matter alone, revealing the presence of dark matter. That discovery confirms Segway 1's true nature. What makes it extraordinary is the scale of that darkness. Its dark matter outweighs its stars by roughly 3,000 to 1. It is, in essence, a shadow-made Selida halo of unseen mass with only a faint dusting of light. Willman 1 is even smaller, containing just a few hundred stars, orbiting the Milky Way at about 120,000 light-years. These ultra-faint dwarfs may be the most common galaxies in existence. For every giant like the Milky Way, there could be hundreds or thousands of these tiny systems scattered through space, unseen because of their distance and dimness. They are also among the oldest structures known. Their stars formed in a single brief surge more than 13 billion years ago. shortly after the Big Bang and then creation ceased. They are true fossils of the early cosmos. Born from gas touched by only the first few supernovae, preserving a universe that no longer exists, yet still speaks through them. Because these ancient systems contain so few heavy elements, their stars act like time capsules. By carefully measuring the exact proportions of each element within them, astronomers can reconstruct what the very first stars were like and how they began enriching the newborn universe. In this way, the faintest galaxies speak most clearly about cosmic origins. For most of human history, none of this was known. When early observers noticed hazy patches of light scattered across the sky, they called them nebulae, believing they were simply clouds of glowing gas embedded within the Milky Way itself. The universe, it seemed, ended at the edges of our galaxy. That illusion shattered in 1923, using the Hooker telescope atop Mount Wilson. Edwin Hubble turned his attention to the Andromeda Nebula. What he saw changed everything. Individual stars resolved themselves within Andromeda, and among them were Cepheid variable stars, stellar beacons that rhythmically brighten and dim. Their pulses follow a strict rule. The slower the pulse, the brighter the star truly is. By measuring that rhythm, Hubble could determine their actual brightness. Comparing it to how faint they appeared from Earth revealed their distance. The result was staggering. Andromeda was not nearby at all. First estimated at 900,000 light-years and, later corrected to about 2.5 million, it lay far beyond the boundaries of the Milky Way. It was not a nebula. It was an entire galaxy of its own. In a single moment, the universe expanded. The cosmos was no longer a lone galaxy surrounded by misty clouds. It was an immense realm filled with countless galaxies, each a city of stars. In 1936, Hubble formally identified 12 galaxies as members of what he called the local system, including the Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and several dwarfs. As instruments sharpened and methods advanced, that list grew. By the mid-20th century, roughly 24 local group members were known. By the century's end, the count reached around 40. Today, astronomers have confirmed approximately 50 to 60 galaxies within our local cosmic family, and the number is still rising. Finding these galaxies, especially the dimmest ones, requires patience and precision. Wide-field telescopes sweep enormous portions of the sky, capturing millions of stars at once. Computer algorithms then sift through the data, searching for subtle, over-densities, tiny gatherings of stars that may betray the presence of a hidden galaxy. Each candidate must be verified, confirmed as a true galaxy rather than a chance alignment, and shown to belong to the local group rather than the distant universe beyond. This search continues through vast surveys. The Sloan Digital Sky Survey transformed the field in the early 2000s, mapping huge regions of the sky and creating databases rich enough to reveal previously unseen galaxies. The Dark Energy Survey extended that legacy. Soon, the Vera C. Rubin Observatory's Legacy Survey of Space and Time will repeatedly image the entire visible sky, potentially uncovering dozens of new ultra-faint dwarf galaxies within the local group over the coming decade. Meanwhile, precision mapping continues. The Hubble Space Telescope still observes Cepheid variables in nearby galaxies, refining our three-dimensional understanding of local space. The European Space Agency's Gaia mission is charting the positions and motions of billions of stars, tracing their orbits and revealing the Milky Way's hidden structure. Gaia has even measured stellar motions inside nearby dwarf galaxies, allowing astronomers to map their dark matter from within. Radio telescopes listen for the 21-centimeter signal of hydrogen, tracing the flow of gas, the raw material of future stars. ALMA peers into cold clouds of dust and gas, where stars are just beginning to form. The James Webb Space Telescope, launched in 2021, looks at infrared light, slipping through dust to reveal ancient stars and concealed nurseries of creation. On Earth, adaptive optics sharpen ground-based telescopes to near space-level clarity. Gravitational wave observatories like LIGO and Virgo detect ripples in space-time from colliding black holes and neutron stars. Neutrino detectors catch ghost-like particles born in stellar explosions. Together, these voices form a single narrative, a layered, living portrait of our galactic neighborhood. Sometimes the past reveals itself directly. In 2020, astronomers analyzing Gaia data identified a vast stream of stars in the Milky Way's halo known as Gaia Enceladus. It is the scattered remains of a massive dwarf galaxy that collided with the Milky Way roughly 10 billion years ago. Even now, its remnants drift through our galaxy, a reminder that the local group is not static, but shaped by ancient encounters written into the stars. This lost galaxy, now known as Gaia Enceladus, or the Gaia sausage, was no minor visitor. It once held several billion stars of its own. When it encountered the Milky Way, the meeting was violent. Gravity tore it apart, scattering its stars into long arcs that now drift through our galaxy's halo. The shock of this discovery lay in its timing. It revealed that the Milky Way experienced a major merger far later than astronomers had once believed. For decades, our galaxy was thought to have lived a relatively peaceful life, growing slowly by absorbing only small dwarf systems. Gaia Enceladus changed that story. It showed that the Milky Way, like other great galaxies, was shaped by powerful collisions. And it is not alone in that history. Andromeda carries similar scars. Within Andromeda's halo, astronomers have found streams and shell-like structures, stellar debris left behind by galaxies it consumed long ago. Among these remnants, one stands out: the Great Southern Stream. This immense river of stars stretches across hundreds of thousands of light-years and is believed to be the remains of a dwarf galaxy destroyed several billion years in the past. These stellar streams function like cosmic ruins. They preserve the memory of galaxies that no longer exist. By tracking the positions and motions of the stars within them, astronomers can rewind time, reconstructing the original orbit of the lost galaxy and estimating its mass, shape, and fate. The past, it turns out, still moves through the present. At the heart of all this motion is a single force: gravity. Within the local group, gravity acts on many levels at once. On the grandest scale, the combined mass of the group pulls all its galaxies toward a shared center of gravity. That center lies between the Milky Way and Andromeda, shifted closer to Andromeda because of its greater mass. On a smaller scale, each major galaxy exerts influence far beyond its visible form. Their gravitational reach extends deep into space, capturing smaller galaxies and binding them into long-lived orbits. And within each galaxy, gravity governs the paths of individual stars as they circle their galactic cores. Yet gravity also revealed a mystery. When astronomers measured how stars move in the outer regions of galaxies, they found speeds that made no sense. Far from the center, stars were orbiting far faster than visible matter alone could explain. According to classical gravity, they should have been moving more slowly, not racing ahead. The only explanation was hidden mass, dark matter, an unseen substance distributed in vast, roughly spherical halos surrounding galaxies. These halos stretch far beyond the luminous disks. The Milky Way's own dark matter halo reaches hundreds of thousands of light-years outward, possibly farther still. Andromeda's halo does the same. In the space between our two galaxies, these invisible envelopes overlap. When dark matter is included, the Milky Way's total mass rises to about 1.5 trillion times the mass of the Sun. Only a small fractioner, around 10%, consists of stars, gas, and dust. The rest remains unseen. Understanding this hidden majority is one of the greatest challenges in modern physics. Its existence is undeniable, revealed by gravity's pull, but its nature remains unknown. Dark matter gives off no light, absorbs none, and reflects nothing. It moves silently, interacting primarily through gravity and perhaps the weak nuclear force. Many possibilities have been proposed, but one candidate has long dominated scientific imagination: the WIMP, a weakly interacting massive particle. Whether this shadowy particle is real or not, its influence shapes galaxies, governs motion, and quietly determines the fate of the local group itself. WIMPs, if they exist, would outweigh protons by a wide margin, yet pass through ordinary matter almost untouched, interacting only on the rarest occasions. Around the world, deep underground experiments wait in silence, hoping to witness the fleeting moment when one of these particles collides with a normal atom. Other possibilities remain open. Dark matter may be made of Ixian exceedingly light particles, or it could consist of primordial black holes, formed not from dying stars, but from density fluctuations in the universe's earliest moments. Gravity's not the only force shaping galaxies, though it reigns supreme. Light itself carries momentum. Every star presses outward through radiation, and when that light strikes gas or dust, it exerts a subtle push. Most of the time, this pressure is insignificant compared to gravity, yet in specific environments, its influence becomes meaningful. In regions where massive stars are being born, intense radiation can squeeze nearby gas clouds, compressing them until new stars ignite. Under extreme conditions, that same radiation can drive gas completely out of a galaxy. This process is believed to help silence dwarf galaxies. Their first generation of massive stars floods the system with light, sweeping away the remaining gas and ending star formation before it can begin anew. Galaxies are also threaded with magnetic fields, woven by the motion of charged particles through hot gas and plasma. These fields are weak compared to gravity, yet they matter on smaller scales. Magnetic pressure can slow or resist the collapse of gas clouds, regulating how quickly stars form. Creation, even on cosmic scales, is restrained as much as it is driven. Many dwarf galaxies bear the marks of gravitational strain. Their stretched or lopsided shapes reveal past encounters with larger neighbors. Some trail long streams of stars, stellar remnants torn away by tidal forces. These streams can endure for billions of years, gradually unraveling as stars drift apart, each carrying a memory of the moment they were pulled free. Dwarfs do not exist in isolation from one another either. When two small galaxies pass nearby, their mutual gravity can disturb their structure and ignite bursts of star formation. Several irregular dwarf galaxies show evidence of such encounters, their recent stellar activity echoing a close gravitational meeting. Gas itself moves between galaxies, shaping their futures. Vast reservoirs of hydrogen lie both inside galaxies and in the space between them. Gravity can draw this gas from one system to another. Supernova shock waves can heat it. Radiation from young stars can ionize it. In one especially powerful process RAM, pressure stripping a dwarf galaxy plunging through hot intergalactic gas can be swept clean of its cold gas, losing the raw material needed to form new stars. This may explain why so many dwarf spheroidals fell silent long ago. Yet even the local group is not alone. It rests near the outskirts of a colossal structure known as the Virgo supercluster, or Laniakea, vast gathering of galaxy groups stretching more than 500 million light-years. The combined gravity of this immense system pulls on us. Relative to the cosmic microwave background, the local group races through space at about 1.3 million miles per hour. Much of that motion driven by forces far beyond our immediate neighborhood. At the heart of this pull lies the Great Attractor, a region of unusually high mass concentration. It draws not only the local group, but hundreds of galaxy clusters toward it. Beyond even that lies the Shapley supercluster, an even greater congregation of matter, exerting its own silent influence across the cosmic web. The local group itself is best understood as a layered structure. At the highest level, it is a collection of galaxies spanning roughly 10 million light-years. Within it lie smaller domain subgroups centered on the Milky Way and Andromeda. Each is a dominant galaxy surrounded by dozens of lesser companions, all bound together, all moving in quiet obedience to gravity's unseen design. At a more refined scale, this structure narrows into individual galaxies each. One, a vast system of billions of stars arranged into disks, central bulges, and extended halos. And deeper still lies the smallest tier, stellar systems themselves. Single stars and the worlds bound to them, planets, moons, asteroids, and comets, each moving within their own delicate balance. Every layer of this cosmic order follows its own rhythm, governed by different physical laws and unfolding across different spans of time. On the scale of stars, change comes relatively swiftly. Stars are born, mature, and perish over millions to billions of years. Planets circle their suns in spans measured in years or decades. Galaxies, by contrast, move to a slower cadence. A single star can take hundreds of millions of years to complete one orbit around its galactic center. Step up again to the scale of the local group, and time stretches further still, unfolding over billions of years. This nested order is not accidental. It is one of the universe's most fundamental patterns. Gravity, acting across immense distances, draws matter together, while time allows structure to emerge. Begin with matter spread almost evenly. Introduce gravity. Wait long enough. The result is hierarchy. Those small clumps form first stars and planets. Those gather into galaxies. Galaxies assemble into groups and clusters. And at the grandest scales, those clusters link together into superclusters and filaments. The local group is one junction within this immense cosmic web, tied to neighboring groups and clusters by invisible threads of dark matter and streams of galaxies. It is not isolated, but woven into a larger design that spans the observable universe. To understand this architecture, astronomers turn to modern cosmological simulations, some of the most complex calculations ever attempted. These simulations do far more than track gravity and dark matter. They incorporate gas dynamics, star formation, the explosive feedback of supernova, stellar winds, radiation, magnetic fields, and even cosmic rays. Running on the world's most powerful supercomputers, they follow billions of particles across cosmic history. By comparing these virtual universes to the real one, scientists test whether their ideas hold true. When simulated galaxies resemble what telescopes observe, matching sizes, shapes, and behaviors, it suggests the underlying theory is sound. One of the greatest triumphs of this method is the CDM model of cosmology. CDM represents our best current explanation of how the universe came to be and how it evolved. Lambda refers to dark energy, the enigmatic force accelerating cosmic expansion. CDM stands for cold dark matter that moves slowly compared to light and provides the gravitational scaffolding for structure. Together, this model successfully explains observations ranging from the faint afterglow of the Big Bang to the vast patterns of galaxies across space. Yet it is not without tension. Some observations resist easy explanation. One of the most persistent puzzles is the missing satellites problem. Simulations predict that a galaxy like the Milky Way should be surrounded by hundreds or even thousands of small dark matter halos. And any of these halos should host stars, appearing as dwarf galaxies. But only a few dozen have been observed. So where are the rest? One possibility is silence rather than absence. Many of these halos may be too small or too fragile to ever ignite stars, rendering them invisible. They exist in darkness, shaping the universe through gravity alone unseen, yet still part of the grand design.